All right, so in this chapter, we're going to talk about momentum. Momentum is defined as the product of the mass and the velocity of a particle. And momentum is clearly a vector because velocity is a vector, mass is a scalar, and the product of a scalar and a vector is always a vector. The symbol for momentum happens to be P. Okay, the unit of momentum is kg meters per second. There is no particular name for this combination of units, it's just called kg meters per second. All right, so that's the definition of momentum. Interestingly, Newton's second law can be written in terms of momentum. So let's see how we would do that. So Newton's second law is net force equals mass times acceleration. Now you know that acceleration can be written as the derivative of the velocity, as you've seen in chapter 3. Now, if the mass is constant, there is no harm in moving it into the derivative. So you know that the rules of derivatives say that if you have a constant quantity multiplying your function, then you can feel free to pull that constant out of the derivative. So here we are putting it back inside the derivative. So this is what we have. F net equals ddt of mv, but we just saw that mv is the momentum. So F net is equal to ddt, or the derivative of the momentum. And so this is Newton's second law. Now you might say that what's the point of doing this? Like, what was wrong with F net equals mass times acceleration? Well, the advantage of doing this is that there might be systems where the mass is not constant. So in all the examples that you've seen in earlier chapters, the mass of an object has always been constant. But you can easily think of examples where the mass of an object is not constant. Can you think of one yourself? Here is one example, a rocket, for instance. When a rocket is flying in space, or anytime the rocket is moving, it gives off exhaust. It shoots off exhaust. So as it's shooting off the exhaust, it's losing a lot of mass. So the mass of the rocket is not constant. So in problems like this where the mass is not constant, you can still apply Newton's second law in the form F net is equal to dp dt. And incidentally, this is the form in which Newton himself presented his second law. F net equals ma is a sort of simplified version of that for cases where the mass is constant. Now, fortunately for you, we will not be going into problems like this, like the rocket problem where the mass is not constant, because those problems are usually pretty hard. I'm just mentioning this so you understand that this form of Newton's second law is more general than F net equals mass times acceleration. All right, now let's define a new concept. So we'll keep coming back to momentum, but let's just learn about a new concept now. And that is the concept of impulse. So the impulse of a force which acts from a time t0 to t is defined like this. Okay, so the impulse is just the integral of the time integral of the force over the period of time that it acts. Right? What's an example of this? So consider a ball which hits a bat, right? So suppose you or a wall or something. So you have this ball that's coming in and it hits the wall. What kind of forces act on it when it hits the wall? A very large force acts on it for sure, and that would make it turn around and bounce back. Is that force a constant force? The answer is no, because when the ball hits the wall, just as it's making contact, the force is small, but then as the ball sort of slams into the wall and squeezes against the wall like this maybe, then the force might be quite large. Then the ball just takes off in the opposite direction, and as it's taking off, the force from the wall would decrease and then become zero when the ball loses contact with the wall, right? So if you wanted to make a graph of this force, if you wanted to make a graph of the force as a function of time against the time that it acts. So the force only starts acting when the ball first makes contact with the wall, and at that time the force is small. But then as the ball squashes against the wall, the force might increase tremendously. And then the ball starts rebounding and going back, and as it begins to take off, the force will decrease, and eventually the ball, at some point, the ball just completely loses contact with the wall and flies off. And at that time, the force becomes zero. So the force would have this kind of time dependence. And the time interval over which the force acted, let's just call that delta t. This is our time axis, and we'll call this time interval as delta t. This is very, very small. So the ball only remains in contact. We are talking about a tennis ball bouncing off of a wall. So the ball only remains in contact with the wall for maybe a few milliseconds or something like that. So it's a very, very small time interval over which the force acts. So what is impulse? The symbol for impulse is J, and as you can see in this chapter, all the symbols are completely off. Symbols and their letters are completely off. Momentum was P, impulse is J. So J is defined as the integral of the force over the time interval that it acts. So if the force acts from t equals 0 to t equals delta t or something like that, then this will just be 0 to delta t. I think in the PowerPoint I say t initial to t final, which really means the same thing. Maybe I'll just do that. T initial to t final, just to make it match with the PowerPoint. So that is the formal definition of impulse. Okay. Now, normally we don't have to actually evaluate this integral. Like if the force is given to you as a function of time, then you can just go ahead and evaluate this integral and find the impulse. But we don't normally have to do this integral, because we are generally satisfied by replacing this variable force by a constant force. So let's just pretend that the force that the wall exerts on the ball is a constant force. So we would just call that F average. So we are replacing the actual force with this constant force. It's easier to replace the actual force by a fictitious constant average force. And what is the impulse for this average force going to be? The good thing is that it's a constant force, so the impulse would just be F average dt, t initial to t final. If F average is a constant, so you can just pull it out of the integration. T dt, t initial to t final. This is a very easy integral to do. Integral dt is just t. So it's going to be F average times t minus t initial. We are just going to call t minus t initial as delta t. So it's F average times delta t. And that is our impulse. So to summarize, if you work with and the impulse is a vector, so strictly speaking, there should be vector signs over all of these. So to summarize, if you work with the actual force, the impulse is simply the integral of the force dt over the time interval that the force acts. You can also write the impulse as F average times delta t, where F average is a fictitious average force that you're using instead of the real force, which has a very complicated time dependence. So F average is a fictitious average force which you're using. And in terms of that, the impulse is simply the average force multiplied by delta t. Now, for all, usually we are happy with just this average force. We don't really care about the details of the actual force that's acting, just because the force is acting for such a short amount of time. So we're just happy with pretending that the force is constant, and just working with this constant average force, right? Okay, so that is the definition of impulse. So impulse is one of these two, either this one or this one, depending on which form of the force you want to work with. Now, how is impulse related to momentum? So we first learned about momentum, now we are learning about impulse. Is there any connection between them? Absolutely. That crucial connection is called the impulse momentum theorem, and that's what we're going to talk about next. So let's write down the formula for the impulse, J, and let's just write down the rigorous formula, f of t dt, t initial to t final, right? Now let's put in Newton's second law. So Newton's second law, as you know, is F net equals dp dt. If the only force acting on a particle is just F, then F net and F are the same thing. So I can just write this as T0 to T dp dt dt. That is J. So P is the momentum of the particle, and the force, the net force acting on the particle, F net, is equal to dp dt. That's Newton's second law, right? So that's all that we did over here. Now, you know that whenever you have a dp dt, that's a derivative, and if you integrate a derivative, you just get back the original function, right? Because you know that differentiation and integration are opposite operations. So if you do dp dt, that means you're taking the derivative, but then if you integrate the derivative, you get back the original function. So this is nothing but p, the original function, evaluated at the two endpoints, t0 and t, right? I hope it's clear what we just did. This is the derivative, dp dt is the derivative, and when you integrate a derivative, you just get back the original function, right? So if you have a function y of x, if you differentiate that, that's dy dx or y prime x, and then if you integrate y prime x, you just get back y, right? So that's exactly what we did. So that is just P final minus P initial, and that is the impulse J. So P final minus P initial is just the change in momentum. The definition of delta, which is change, is just P final minus initial. So you get this very important relation that J, the impulse, is equal to the change of momentum, and that is the connection between impulse and momentum. Impulse is equal to the change of momentum. All right, so that's the impulse momentum theorem. Let's look at a quick illustration of the impulse momentum theorem. Let's take a look at this problem, and please try this problem. Pause the video and try this problem yourself, and then we will then look at how I work it out. So this is slide 4. It's saying that a 100 Newton force acts on a bullet in the barrel of a gun. So here is the barrel of the gun. Okay. And the bullet is somewhere at the back over here. So what happens inside a gun? You have an explosion, right? And that causes rapidly expanding gases, and those gases exert a force on the bullet and exert a tremendous amount of force on the bullet. That force acts on the bullet while it's still in the barrel of the gun, and then the bullet emerges from the, what's this thing called, from the opening here with a very high velocity, right? So that's how a gun works. So what the problem is saying that while the bullet is inside the barrel of the gun, it's feeling this 100 Newton force, uh, and you're given the mass of the bullet, uh, and you're also told how long it stays inside the barrel of the gun, right? So let's try the first part. Calculate the acceleration of the bullet. So to find the acceleration of the bullet, you can just use Newton's second law. So the force, there's only one force acting on the bullet. We are going to ignore friction and all that. So there's only one force acting on the bullet. That's the 100 newtons, right? So applying Newton's second law, since we are ignoring friction, so net force would just be F. So applying Newton's second law, you get F equals ma, or A is equal to F divided by m. So 100 newtons divided by the mass of the bullet, which is 0.01 kgs. So this is going to be 100 newtons divided by kgs. So newtons is kg meters per second square, as you remember from chapter 5. And if you divide that by kgs, then the kg cancels out and you get 100 actually this is 10,000. I shouldn't have this comma here. Meters per second square. So that's the acceleration of the bullet. So very high acceleration. Okay. So the question is, what is the okay? So that's the first part, right? Okay. So there was nothing new here. It's just application of Newton's second law. Calculate the bullet's final velocity. So the final velocity of the bullet as it emerges from the gun, that is something you can calculate just using kinematics. So you know the initial velocity of the bullet, which was 0. You know the acceleration, you know the time. So you can use this equation v final equals v initial plus acceleration multiplied by time. So v final is what we are looking for. V initial is 0, acceleration is 100, 10,000 multiplied by the time, which is 0.5 seconds. And so this is meters per second square, and this is seconds, so the answer is going to be in seconds. So this is going to be 5,000 meters per second. Okay. 5,000 meters per second. So, all right, so this parts A and B are just a review of stuff that's happened in previous chapters. So there is nothing new so far. Let's calculate the bullet's change in momentum. So the change in momentum delta P is always P final minus P initial. I should just stick with my notation here. I always use no subscript for final and 0 subscript for initial. The initial momentum was 0. What about the final momentum? The final momentum is mass of the bullet, which is 0.01 kgs, multiplied by the velocity of the bullet, which is 5,000 meters per second. And so that's just going to be 50 kg meters per second. So that is the change in momentum, right? Now let's calculate the impulse experienced by the bullet. The impulse is going to be force multiplied by the time that the force acts for, right? In this case, the force is constant. So so the impulse, the impulse is the integral of the force. But if the force is constant, it just becomes force multiplied by delta t, as we've seen over here. So if the force is constant, or if we can pretend that the force is constant, then the impulse is just force multiplied by the time over which it acts, right? So in this case, the force is given to be constant. So it's just going to be 100 newtons multiplied by the time that the force acts for, which is 0.5 seconds. So this is going to be 50 Newton seconds. And you can easily convince yourself that Newton seconds is the same thing as kg meters per second, because Newtons is kg meters per second square. If you multiply that by seconds, then one of these cancels out, so it's kg meters per second. And so this just shows you that the impulse momentum theorem is true. You get the same answer. So this just shows you that J is the same thing as delta P. All right, so just a quick demonstration of the impulse momentum theorem.